Oh, we can email it to you, right?
So,
We can email it to someone.
Yeah.
I was gonna say I'm emailing right now.
okay, folks, so let me say a couple words about next.
Oh, yeah. I can check it.
This is not.
I was gonna say, I'm like, I don't know much. We're not doing that.
I'll say stop sharing. There we go. All right, let's say a couple words about your next homework. Here, we will let P and Q be projected R modules. What I want you to do is show the tensor product. P and Q is projected. This is not a problem, we'll not put that. For the second one, you all had localization when you did 8510, right? This is sort of how you localize module. Look at the set S inverse N, which is fractions N over S, where N is in the module and S is in the multiplicative set. And I'm going to declare the two fractions. So really I have elements of the module divided by, something in the multiplicative set. If you saw localizations, then you saw that you've got a similar thing here. We said the two fractions N1 over S1 is equal to N2 over S2. If and only if there's a T and S such that you have the cross multiple, right? S2 N1 minus S1 N2. If you can multiply that by a T in the multiplicative set 0, then that's what it means for two things to be equal. Everybody okay with that? And you add two things the same way you would think and multiply. Something hard, the way you would think. Of course, it doesn't really make any sense to multiply N over S and N prime over S prime, does it? Because N prime might not make any sense because you're talking about an R module. But other than that, you're golden. So this setup is kind of a theme. I promised you we'd talk a little bit about flatness in the homework. Localization is flat. So I'm going to make this a little bit easier. R is an integral domain, and N is an R module, and S is a multiplicative subset of R. First exercise, show that everything in R localized at S tensor N, tensoring over R, can be written as a single tensor of the form 1 over S tensor. This is going to be useful in the problems that follow. Number B, show that there's an isomorphism between RS tensor R of N and S inverse. So you can think of this as when you take, sometimes they call this sort of thing extension of scalars. If you take N and you tensor it over R with R localized at S, it's this, you're sort of allowing fractions in your module in a certain sense. Show that a tensor of the form 1 over S tensor N is 0. If and only if there exists a T in S since T in 0. So that's kind of a nice thing. That depends on the previous. Use this all to show that R localized at S is a flat R module. So this shows that if you have a localization, that the localization RS is flat as a module over R. Here's the five localization flat. And finally, show the Q is a flat Z module that's not projective. The flatness is now elementary to part D, but what you need to do is show that Q is in fact not projective. Number 3, suppose R is an integral domain, push it to OK, and M an R module. let Tm, the set of x and n such that Rx equals 0 for some R and R. This is called the torsion module. It's the set of things in N that are killed by a non-zero element of R. We've seen in an earlier exercise that Tm is actually a submodule then if R is an integral domain. Show that M mod Tm is torsion free, and what I mean by that is the only torsion element is 0. And show, I like to call this tensoring, tensoring with the torsion field kills torsion. If you take M and you tensor it with the quotient field bar, you get M mod Tm tensor ball. So I'll show you an example of kind of how that works at the moment. And for adjoint associativity, we talked about this earlier. We talked about the maps in both directions. Show me this one, if R is a commutative ring of identity, A, B, and C are R modules. Show that we have this isomorphism of R modules from home, the tensor product of A and B to C, into the homomorphism from A to the homomorphisms from B to C. Okay, any questions on that? Before I go on into what we've been doing here, I do want to do an example that I keep going on this example for several days. This is but we've already started on the business with the modules over at PID, but I don't think it's going to hurt if we go back and talk about this one just a bit. And this might help in the spirit of problems. See if I know what I mean by torsion abelian group. Actually, it means it's a torsion module, as I said in the homework, with as a Z module. This means for all A in A, there exists still is it an abelian group I'm going to think of as a Z module. And so what this means is that there's a non-zero natural number that kills A. Another way to think of this is every element. Here's a way to think about it. A is a non-zero. Right, I mean, that's essentially what it's saying. This means that the order of A is a divisor of N. Everybody agree with that? Okay. Now, watch what happens. What if I take my torsion part here, torsion part. What are you supposed to happen here? Tensor with group with Q, it kills it. So I'm going to make this claim. Proof. Anyway, what do you know about A? Well, A is an element of a torsion group, so there exists I agree with that. Now, what I feel so slimy doing this. Same rational number, right? Nothing up my sleeve. And this is in a tensor Q over N, still a rational number, which is 0. So all tensors are 0. So a tensor goes it's everything in there is generated by the tensors, and they're all 0. So this is actually important in algebraic topology and things like this. Is tensoring something with Q kills the torsion. And that's actually, you were to show that in a more general situation. Yes. I'm sorry, why?
Why n times a is 0?
Ah. Because this is a torsion abelian group.
Oh,
Right, so every element A is a finite order. Okay, let me kind of, the last thing that we had is, if R is a PID and F, is a free R module, then, any submodule, let's call it, E, has property that E is free and rank E is no more than rank F. Right, and we had a couple of corollaries that I will call Ruby on. Corollary 713. If you have a PID and A is an ungenerated module, then any submodule A can be generated. By M plus center equal M elements. And the other one I had corollary 784 was if P, well, say parts of PID and P is an R module, then P projected if and only if P. Okay, so why are these true? I think this is actually easy. Free and public projective always, but why does the other way work? Yeah, How about the other question? What's one characterization of projective modules with, in comparison, say, to free modules? Modules projected if and only if it is a it's a direct sum into the free. It's supposed to be the projective. Then there exists R mod K such that P sum K but no. So there exists injective homomorphism B from E into F. So P is isomorphic to a submodule of a free of F, a free R mod. Therefore, if, and that uses this result here that any submodule of free is free. P is projective, it's isomorphic to a submodule of free module, so it must. So you gotta love that. How about the other one? The other one's a more general statement. Just that A is finitely generated. So this doesn't, I don't have anything in that hypothesis here about freeness or anything like that. If A is any n-generated R module, then it's the submodule of, well, I'm sorry, if A is any n-generated R module, then any submodule that you can find of A is generated by n elements or less. Right? Any idea on how to prove this one? Let me ask you a question. Suppose A suppose A is generated by these elements. Gosh, I guess we're going to use that crap about free modules, right? So what's this got to do with freeness? Remember, free modules are like God, and all other modules are created in the image of God, right? So this is the homomorphic image of a free R module, right? And in fact, can you do better than that? Not only is it the homomorphic image of some free R module, can you right? In fact, I can use exactly in general. So A R module, which can be chosen as in generator. In fact, that's or mapping property of free modules. In fact, suppose I take F to be equal to you could set the map up such that if you take the basis of this to be standard basis, like E1 is 1, 0, 0, E2 is 0, 1, 0, 2, etc. You could take E1 to X1, E2 to X2, and so on. Okay. Now, let's let now would be a submodule A. I want to show that B can be generated by n elements or less. Any ideas how I might go about this? See the pre-image of this model here. This is the set of everything over here that lands in B. This submodule. And what does the theorem tell us? Well, this is the rank of T inverse V is less than or equal to the rank of F plus E. So this means free and generated by, say, Y1, Y2, Ym, with M less than or equal to F. So finish off this claim. I claim B is equal to I claim that any element of B can be expressed, can be generated by those M elements. Let B be B. Since B is onto, there exists Z such that P of Z equals B. Because of the fact that the homomorphism is on. Also, what do you know about Z? By definition, Z is in Phi inverse V. By the way, I didn't prove that this was an R module, but I think it's pretty standard. See if you can show that. It's not. Z is in Phi inverse V, so Z is equal to R1 Y1 plus R2 Y2 plus R M Y M with RI, because everything in here is generated by this basis. Therefore, P, which is P of Z, is equal to R1 P Y1 plus R M P Y M. So, so what we've shown is B is contained in this, and since these things are all in B, the other containment is obvious. So B generated by plus something. Any questions on that? Okay, here's kind of a neat theorem. And this, again, you've probably seen something like this before in 8510 or maybe even earlier when you did the fundamental theorem of finite generated abelian groups. Any finitely generated torsion-free model over a PID. So your earlier version might have been said over the integer, or it might have even said any finitely generated torsion-free abelian group. Um, Torsion-free is maybe the more obvious you need this thing going on, right? I mean, if you just take a simple example like Z and look at some torsion module, right, like Z6, well, Z6 over Z is never going to even have a basis, right? Because everything in Z6 over Z is linearly dependent. Multiply anything by 6, you get 0, right? So that one's a little bit easier to see why you want to lump that in there. What about finitely generated? Can anybody give me an example torsion-free module? Over Z, well, let's just say over Z. Give me an example of torsion-free module over Z. That's not free. That's an example. Q. Q is a good example of this, and you're going to see this in the next homework. But for example, Q is torsion-free, the torsion in it, but it's not finitely generated. Now, of course, there are modules that are not finitely generated that are free. For example, just take a direct sum of them, infinitely many copies of Z, and that'll work. But without this assumption, you're not guaranteed generality. So let's do this. Let A be finitely generated and torsion-free. And we'll say that it's generated by the set of elements here. And our assumption is finitely generated is kind of recorded there for us, and it's also torsion-free. Since A is torsion-free, each psi is a linearly independent set. Just as a singleton, because Rxi equals 0 implies R. So each one of those singleton sets just by themselves form a linearly independent set. Let's suppose and you might have to reorder if necessary. That the set x1 up to xk my point would be a subset of x. And here, of course, a. By the way, let me point out that this set, this is a generating set, so we know that it spans A. If this also, if we get lucky enough that this is linearly independent, we're done, because then it's free, right? Well, I know that the singleton sets are linearly independent. So if nothing else, this might, I mean, it might be the case that K is 1, but I'm going to extract a linearly independent subset that's as big as I possibly can. So look at what this linearly independent set generates, and it will generate a free module because this is again a spanning set of a spanning set F by definition, and it's a linearly independent set. So this is a free submodule of A. Let me point out that if of course, this is a possibility. Let me point out that when I did build the original generating set, I did not tell you that it was as efficient as possible. I might have some superfluous generators in here I don't need, and I might get lucky. And even though this is a smaller set, this might still generate all of A if I wasn't efficient in the first. So if I get lucky, then I'm done. And A is free. If not, then I can assume that that X efficient right impose XJ is not in F for but for each J, there exists R sub j and R such that okay. So let's justify that. Why is this the case? Well, I'm claiming for each one of these J's is outside of that period. So these elements that are outside my maximal set, there has to be an RJ such that this is true. And I can assume that RJ is not zero. Yeah. Why is that? Well, that's right, because if you take x1, x2, xk, xj, right? This is linearly dependent. Let's be linearly dependent, right? So we can find R1, R2, RK, RJ, such that R1, X1, R2, X2, RK, XK, RJ, XJ, 0, and not all RI 0. Right? Everybody agree with that? Note if RJ equals 0, then R1, R2, to RK equals 0. Right? Because if this one is 0, then you're back to your linearly independent set, and that forces all the other ones to be 0. Right? So you can assume in this relation that RJ is not 0, because if it is, it forces all the other RIs to be 0. Once you have this RJ not 0, take this stuff and chuck it over the other side, and you get that equation. Okay. Everybody okay with that? Now, let's R J, I'm sorry, RK plus 1, RK plus 2, R. Anybody want to make a observation about that step? This definitely depends on finite generation, doesn't it? Right, because I'm multiplying together a bunch of R's, right? Then they correspond to my basis elements, my generating set. If this were not finitely generated, in other words, if I had infinitely many R's to deal with, I couldn't do this. So this point right here really kind of underscores finitely generated. Finitely generated is very important at this juncture. Okay, so let's see if we can finish this off. let me point out that when you take this R, the product of these other things. Recall that X was the set. Notice that Rx. R times X lands you in F. Why is that true? Well, it's pretty obvious for the first K because the K's are already in F. Right? But look at these relations right here. When you hit XJ with RJ, this is in F on this side, right? So when you hit RJ with XJ, it lands you in here. How did I solve the problem about there's different XJs? I just multiplied everything together, right? So this has an RK plus 1 factor in here, which knocks that into F. And the other ones just push it further. And finally, all the way up, the final term in this product is Rn, which knocks this into F. And the rest of them don't hurt. Right? Are you okay with that? So, in particular, you have that R times A is a submodule of F. And consider the map phi from A to F given by phi of A is R. Because notice everything in A is a linear combination of the X's, all the X's, but R kicks all the X's into F. So this actually, because of this here, this actually goes into F. Notice that the kernel of P is a set of A and A such that R A equals 0. But since A is torsion free, A is equal to 0. So A is isomorphic to phi of A, which is a submodule of F. Since phi of A is a submodule of a free module over a PID, sorry, then phi of A and hence A is. So that establishes the theorem. If you have a finitely generated torsion-free module with PID, it has to be free. We get a nice corollary to this. And next time we can get to forms perhaps. Corollary. If you have a finitely generated module over a PID, 716. Generated. Then you can decompose A into a free part and a torsion. Here's isomorphic to F. So A, where E and finally. So F is free of finite rank and F is isomorphic to A mod. Um, any ideas how we might prove this? Let's prove. Collect all the torsion elements. We've seen that this is actually a submodel. So that's 1-to-1, because this is a submodel. Yes. Let me make the sequence exact. See, I told you this. So this is inclusion, and this is projection. A goes right? A mod AT is torsion free. So this piece is torsion free. And A mod AT is finitely generated. Because A is finitely generated and A mod AT, that's a homomorphic image, so it has to be finite. Everybody okay with that? So what do we know from the previous result? A mod AT is torsion free, finitely generated. So it's free. That's what the previous result says, right? Everybody agree with that? And any free is projected. So this sequence splits. That thing's free, so it's projected, sequence splits, and A is isomorphic to AT, correct sum A mod A. And there's your free part. Okay, it's a good place to quit. Any questions? Questions on that? All right, well, if not, a let me encourage you all to go to the math club today.